we are talking about rectifier circuits, and we saw that what happens if you use a diode and a resistor, right? This is the example you may have, most of you may have come across, where you have a diode circuit and a rectifier circuit, right? A diode with a resistor circuit, right? That is the simplest one to understand, and which all of you already know about. Both half wave as well as full bridge, right? The one on the left, the one on the right. Then last time we had a look at what happens if the load is not only resistance, but it's a combination of resistance and inductor, which is what would be the case in any practical situation, because you may not have a perfect resistance, right? We saw the example of a rheostat which has like coils, right? So it will have an inductance. So if you have a resistance and inductor, combination of both, then we saw that left side, this is how the waveforms would look like, right? This would still work as a rectifier, but now you can see the output average voltage would be lesser than what it would have been if you had a pure resistance, right? The average voltage now, if you see, because the output voltage is going into the negative side also, so the average voltage of the output is little less as compared to what it was before, right? And if I keep increasing the inductor, right, and I make inductor very large and there is no resistance, then you saw that output voltage will actually be sinusoidal and the average value will be equal to 0. So if you are thinking of this rectifier as an AC to DC, converter, then just a pure inductor, it would no longer behave as a rectifier, right? A combination of L and R, it would still behave as a rectifier. You may have some negative voltage, but you will get an average DC value, right? Next is, what if the load, so there are these types of common load, right? Resistive is one, L and R combination could be a rheostat, could be a motor kind of a load, for example, right? Any motor winding would have an inductance and resistance, right? The third common type of load is a capacitive load, right? So what if you have this kind of a circuit where you have an AC source, a single diode, and then followed by a capacitor, and then parallel to a resistance, right? What would be the waveforms in this case? What would be the output voltage waveform? What would be the current waveform in this case? So let's do that. So let's say this is V in, right? Let me mark this as VO, and the current flowing through the diode is, let's say, ID. If this is my input voltage, how would be the output voltage? Now let's say we are starting everything at t equal to 0, right? So at t equal to 0, the circuit was completely de-energized, the capacitor was discharged, everything was discharged, right? And at t equal to 0, we have started this circuit. So what will happen to output voltage going from t equal to 0? Now if I use the timeline in the previous lecture, we were calling it T1, T2, T3, T4, right, as different instants. In this case, because we know this is, for total 360 degrees, so I can call this instant as 2 pi, this instant as pi, this as pi by 2, right? So I can sort of use these notations as well. Or if you want to represent in time, assuming it's a 50 Hz signal, then the total duration is how much? If it's a 50 Hz signal, what is the total duration? How much is the total duration? Difficult question? Huh? Excellent answer. 20 millisecond, then the midpoint would be 10 millisecond, this would be 5 milliseconds, right? So you can represent the timeline in whichever fashion you want. Okay, so what happens between 0 to pi by 2? What happens between 0 to pi by 2? What would be the output voltage? How would the output voltage look like? How would the output voltage look like? Can you answer? Not you, the person in front of you. Yes. Next person. Yeah. How would the output voltage look like from 0 to pi by 2? No? Okay, next person. Person in front of him. Yeah. Sorry? it will follow the input, right? Because the output capacitor initially is discharged, right? The diode will turn on. As soon as the diode turns on, the input and the output is like short circuit basically, right? So whatever is the input voltage becomes equal to the output voltage. If diode is on, V in is equal to V naught. So from 0 to pi by 2, the capacitor would charge, right, from the supply, and the voltage will increase. So 0 to pi by 2, we have voltage, output voltage following the input voltage, right? From pi by 2 onwards, what would happen? That is the main part, right? If this would have, there would have been no capacitor, right? Only resistance, then you know what will happen? The output voltage will be like this, right? It will just follow the input voltage. If there is no resistance, there is only capacitor, then what would have been the output voltage? If there is no resistance, only capacitor, then what would have been the output voltage? Straight line, because now let us say the output voltage is charged to the peak. Peak is, let us say, 325 volt, right? So output is 325, input is now reducing. So diode goes into reverse bias because the voltage across anode and cathode becomes negative. So the diode will just remain off and the output voltage will remain as it is, right? So if it would have been pure capacitor, your output voltage would have ideally remained as it is forever. But now neither, your case is somewhere in between the two, right? So what will happen? Your output voltage will start following something like this. Is that okay? Right? Essentially it is an RC circuit now because the diode is turned off, because for diode to turn on, the output voltage must be following the sinusoidal contour, right, which is not. So the output voltage is still at any instant from pi by 2 to pi is more than what it requires for the diode to turn on, right, and therefore diode remains off in this period and the output RC circuit sort of discharges with the time constant of R into C. It is not exactly a straight line, it is a RC discharge kind of a waveform. So in this period D is on, in this period D is off, and so far let us say we have drawn up to pi. Okay. Any question so far? Any doubt? Yeah, this is the what I have drawn is just an RC discharge curve. Yeah. Any doubt? No, inductor also, of course there is a naturally there is a capacitor, there was an inductor. So we just drawn it with first principle, it appears that there is a phase difference. But if you really see, the phase difference is defined if you have sinusoidal quantities, right? If I have A sin omega t, if I have A sin omega t minus theta, then yes, there is a phase difference, right? If you do not have sinusoidal quantities, then the phase itself is not defined. So to say quote unquote there is a phase difference is it's not a right correct sentence, right? If you have two sinusoidal, if you have only inductor, yes, there is a phase difference between current and voltage. If you have only capacitor, you have phase difference between current and voltage, perfectly fine. But here you no longer have sinusoidal voltages and currents at the output side, right? So actually that phase difference terminology may no longer apply here anyways, right? So last time also I think one of the students did mention that, oh, there is a phase difference because the peak comes later, because peak was coming late, which was fine, but then I do not think the terminology phase difference fits in well for non-sinusoidal quantities, right. So let us not use it, let us just go by basic circuit analysis, because these are non-linear circuits, right. These are no longer linear circuits, you no longer have a sinusoidal outputs. Any other doubt? No, peak is at pi by 2. That is what I am saying, do not try to apply the sinusoidal phenomena here, because you no longer have a sinusoidal current and voltage. Will be because there is no series resistance I have added. If you add a series resistance, then what you are saying may make sense. But here I have not added any series resistance, right. So capacitor is just in parallel to the input voltage. Any other doubt? Yeah. स्लोप तो नेगेटिव ही है शुरू में भी और बाद में भी, फुल From pi by 2 to pi, slope is always negative. Cut to nahi kar payega. It will never be able to cut, na, because as soon as the output voltage goes below it, your input will charge it. So it will never cross it. Right? If you have your resistance value very, very large and capacitor very small, it will at best follow it. But if your RNC is such that in between, so there will be a line in between basically. It will never cut, it will never be able to cross it. Yes. Iski slope 0 hai. Okay. So it will just hold on to the peak value for some more time till this slope starts becoming negative. You get the point? It will never cross. So if you zoom into that pi by 2 section, maybe it will slightly try to follow it for some time and then it will come off. Right? Is that okay? Let's not go into micro details, but more or less this is how the waveform would look like. Now the question is, what happens after pi? What happens after pi? What happens after pi? The next person? Okay. Yeah, the diode will remain off because the anode is at a negative potential because of both voltages, because V in is already negative and the output voltage at cathode is already positive. So VAK will still remain negative, right? So diode will remain off and therefore the RC circuit would continue to discharge, right? So let's say the RC guy continue to discharge. Yeah. Yeah, that's what. Yeah. Yes. Till pi it will follow sinusoidal, yes. Yeah. So I'm just drawing multiple possibilities, right? So you see, depending on time constant, you can have different possibilities here. And then let's say this is possibility A and this is possibility B, where A is, it's somewhere in between and you discharge it and it comes to 0. B is that it doesn't come and discharge to 0. And the next cycle now starts from here. Once the next cycle starts, if you had only resistance, you would have followed this dotted line, right? But if you consider case B, then your capacitor voltage is more than the input voltage at t equal to 2 pi. And therefore, your diode will remain reverse bias, right? Because your output voltage is more than the input voltage. Case B, I am talking about case B, right? In case B, your output voltage at 2 pi is still non-zero, at input voltage is 0. So still your anode to cathode potential is negative. So still your diode remains turned off till the two guys match to each other, and then again it will charge, and then again it will discharge, whatever, and then again it will charge, and then again it will discharge, and again it will charge. Right? That's how, if you have case B, that's how the waveforms would look like. Right? If you had case A, then of course, after case A, it would have started conducting at 2 pi itself. So if you had case A, your output would have started conducting at 2 pi itself and again would have, just repeatedly followed the same waveforms. Most of the places, if you see, typically the time constant is large enough for this RC circuit, and therefore although A is a possibility, but then in reality you never see A when these kind of circuits are used. You mostly see B, and B also with a very small ripple. So the capacitor discharge only slightly and then again gets charged, then discharge very slightly, then again gets charged, right? So in reality, B is what you would observe, and therefore most of the books, most of the literature you see, you would be shown B. Most likely will never be shown A. Okay, now questions? Case A will remain 0 for some time, then it will start at 2 pi again and repeat. Maybe RC will, the slope will become lesser and lesser, and yeah, that's fine. Yeah, that's true. Practically it may not, but then maybe, by looking at it, it would appear more or less coming at 0, right? And then again starting at 2 pi. But I agree, because it's RC by naturally. No sharp point. because if the sharp points try to be there, your input will charge. Na? Okay, I'll zoom it. I'll zoom it and try to show you. Let's do that. So what I think some of the guys are saying that at pi by 2, if it's an RC circuit, right, the slope should be maximum. The slope should be maximum because your maximum voltage, capacitor is charged to maximum voltage, so the current is maximum, slope should be maximum, and as we move forward, the slope should reduce, right? So I think that's why, some of you are getting the feeling that at pi by 2, you should have a sharp drop. I mean, I agree slope should be maximum, but that doesn't mean sharp drop. So what would really happen if I zoom it is, if this is how the voltage, input voltage is, then, and this is the output voltage, this is the peak. After the peak, it will continue till some time, and then it will, do that. That's what, if you zoom it, this is what you would observe. Last time we talked about circuit simulator, go back, try to simulate it and see yourself. That would help you. There's no sharp falling. Yeah. Case A was for a lower time constant, case B is higher time constant. Practically, I'll tell you what happens is, let's say you are using this rectifier circuit to charge your mobile phone, right? Now, what do you want? The 5 volt which is coming to your phone should have very small amount of ripple. It should be more or less 5 volt constant. So, ideally, you want the capacitance to be infinitely large, right? And resistance is the load which is determined by the phone itself, right? So, you don't have much say to that. So, as a power supply designer, you want the capacitor to be really, really large. So, therefore, it will not even be B, it will be something above B in a way, right? Okay, good that you brought this up. So, what she is saying is, if you use a very large capacitance, then there is a possibility for diode to get damaged. Maybe she heard it somewhere. We have not talked about it yet, but she has heard it somewhere. Do you see that as a possibility in this circuit? First of all, that is the question she is asking. You have to think about it. Okay, now what happens is, if I draw the input current, right, then, and if I look at case B, right, this is the region when diode is conducting. So, diode is only conducting this region, so you can have current only in this region, right. Everywhere else current will be 0. Is that okay, right? If you want to find out how the current will be in this direction, it will be, you can write the Kirchhoff's current law. So, the current input will have two components, IC plus IR, right, where this is IR, this is IC, and IC, I equal to C dV by dt, so it will be C dV C by dt plus IR will nothing be Vc by R. Right. So, you can approximately understand that you can even draw the waveform, approximate waveform. So, there will be a Vc by R term which will be similar shaped as that of the input voltage, and there will be a derivative term, right. So, the beginning it will start from here, there is a large slope, so this value may be there, suddenly the current will go up. The first term will start reducing, the second term will start increasing. So, the combination of two, I think could be something like this maybe, I do not know. Does it make sense? Or it could be something like this also, right, depending on the values of R and C, of course, right. Whatever be the case, you will have current only in this region, right. So, if you have value of C large enough, then your region of current becomes smaller and smaller, right. Then the region of diode conduction becomes smaller and smaller, right. If I had a large capacitor, then practically this would conduct only for very, very small time. The output resistance is the same. So, the output power V square by R remains the same. And for power balance, now even if the duration of the input current is very small, the magnitude has to grow up, because the power output is equal to power input, right. So, if the output power, the load power, which is V square by R, remains the same, because I am not changing R, I am only changing the capacitor, right. So therefore the input power should also increase. So if I am increasing C, reducing the duration, my peak value or this magnitude will move up, right? And you have more current coming from input, so you may feel like it will end up damaging the diode. It doesn't do that in practical because the diodes have a very large peak current handling capacities. There are inductances in the circuit also in real circuit, so the current never becomes very, very large. So that's not much of a concern. The bigger concern is that if you start drawing this kind of a current from the input side, the source may not like it. The source may not like it. This is something which we discussed I think last time also. So for example, this current if you are drawing from the grid, right, then there is wire which is going from this room till the transformer, right. Now that wire is carrying this kind of peaky current. What will happen is it will create a voltage drop in that wire which is also of the same nature. So the voltage that you are getting in this room will start distorting, and you would not prefer to have that kind of voltage in this room, right. So it's rather than the constraint on diode getting damaged, it's more of a something what we call it as power quality, and we'll talk more about it in the later half of the course, where power quality defines the quality of the voltage and the quality of the power that we are receiving, right. So if the C is large enough, the power quality may deteriorate, or rather the voltage quality may deteriorate, but that's something which we'll dig upon later, right. Let's not get into it now. So for now, I think what you should be able to understand is that if there is a capacitor and resistance, this is how the general wave shape is. If at all I ask you to find expressions for current or for voltages, these are basic RC circuits. You can always write equations and you can express it, right. If I give you values, for example, in this case, you can do it. You can go back and also simulate and then see for yourself how the different waveforms comes out to be. Yep. Yeah, of course. I don't remember that part. Maybe we can discuss it later. But yeah, of course. If you have an RNC, you can see that the output voltage average is not the same as what you would if you would have had only R, right? In fact, the output voltage average would be very, very close to 325, which is the peak value of the input voltage in this case, right? So if you had R, it would have been average of half sinusoid. If you had an capacitor, it is almost going to remain at the peak with small ripple. So your average will be very close to 325, slightly less than 325, right? So the output average, this is the symbol I would use for average quite frequently, is let's say slightly close, very close to 325 volt, right? Just slightly close and maybe little less than the 325 volt, right, in this case. Alright. In reality, this is the circuit which gets used in most of the rectifier circuit, not the half wave one, but a full bridge followed by a capacitor. Full bridge followed by capacitor, right? So this is, you have this full bridge circuit followed by capacitor. If you look at your mobile chargers, right, this is the circuit which is used. This is the circuit which gets used, and of course this then goes into different sort of loads and everything else within the mobile charger. Okay. Let's now come back and think about this guy here which we were studying in the last lecture, right. Now this is a little bit more than diode, we saw it, right. Yeah, this guy was a little bit more than diode. If you remember, there was this control grid with which I can keep it off for some time and I can turn it on when I want. Once it is on, it behaves like a diode. It will naturally turn off whenever the anode to cathode potential becomes negative, right. This was the mercury arc wall, right, which we discussed before. Do you guys remember it? To turn it on, if you have anode greater than cathode and if you don't have any control grid, it will turn on. If you had a control grid, you can maintain a potential, negative potential, so that the electrons will not flow through it, so it will remain off. As soon as you give a positive potential to the grid, it will turn on. Once it is turned on, it will behave as a diode. Giving a negative voltage to the grid will not make any sense because now there is a huge arc, huge flow of electrons, right. It will turn off only when the anode to cathode voltage becomes negative. right? Do you all remember that? Anyone who wants me to repeat this part? And that's the reason we call it semi-controlled, right? If you recall, that's the reason we call it semi-controlled, because you can turn on, you cannot turn it off. This is a circuit, this is a symbol which is popularly used for this kind of a device, which is a semi-controlled device. There is an anode, there is a cathode, and there is a gate, right? So, if you give a positive potential or a positive current in the gate, this device will turn on. If you do not give that, this device will remain off, even if the anode to cathode becomes positive. Let us look at this circuit. So, you have an input voltage, same exercise we want to draw the output voltage. So, you have an input voltage, ideally my output voltage, if this would have been a diode, the output voltage would have looked something like this, right? If this would have been the diode, this would have been the output voltage, because you have only resistance. Is that okay? Now, because I have, instead of resistance, I have this semi-controlled device, output voltage will depend on where I provide the gate signal. If I provide the gate signal at t equal to 0, this is Ig. If I provide a gate current at t equal to 0, that means I turn on the device at t equal to 0, then how would the output voltage look like? At t equal to 0, if I get a gate signal, anode to cathode is positive, output resistance current is 0, it will turn on and it will give me the same waveform as that of the input voltage, right? And then it will remain 0 because half wave, and then again the same waveform. Given that if I give again Ig here, if I give Ig here, right, it will give me the same waveform. Now, what happens if I do not give Ig at the beginning, but I give Ig little bit later, let us say somewhere in the middle of this section, this is where I give Ig. So, before I give Ig, this will behave as an open circuit, right? It will not allow any current to flow between anode to cathode. Cathode to anode anyways current cannot flow. Anode to cathode also it will not allow any current to flow, because there is a grid there which is not allowing electrons to flow through it, right? So, the output voltage will remain 0. As soon as I give the gate current and anode to cathode is positive, there will be an arc which will get established, right? And now that this is like a forward biased diode, so the output voltage will exactly follow the input voltage. It will hit the peak and then it will come back. It will come back to 0, and then after 0 the diode, since it is a diode, it naturally turns off. It remains off. Again, if I, depending on wherever I give the gate current Ig, right, depending on where I give Ig, it will again from that point itself it will turn on and it will again come to 0, and then I can keep repeating. I have to keep giving Ig at every sinusoidal, right, and this will keep repeating. You want me to repeat this part? So, I can control when I am turning on the device by providing a gate current or a gate voltage, but I cannot control when it is going to turn off. That is the natural diode turn off whenever it happens. Is that okay? They are not the same. After turn on they become same because the device is now on. Before turn on they are different. Yeah? Okay. Any other doubt? Yeah, when the current becomes 0, right, the arc extinguishes and it just becomes off. You can imagine, right, there was an arc, current was flowing, current becomes 0, the arc extinguishes, it just turns off, right? Yeah. Okay, so that's a good question. Just give me a few minutes, let me ask few more questions, then we'll come back to this question. What he's asking is, what if you supply Ig when the current or the voltage is negative? How will this behave, right? So we'll come back to that. But is there any doubt in this particular waveform that we have drawn? So if I give Ig at pi by 2, then my output voltage will start from the peak, right? If I give Ig at pi by 2, then my output voltage will be like this. Yeah. If I give Ig at pi by 2, this is how the waveform would look like. If I give Ig at more than pi by 2, then this is how the waveform would look like. Is that okay? This is Ig at pi by 2, not Ig equal to pi by 2, this is Ig at pi by 2. That means I am turning on that device at pi by 2. Here I am providing Ig at greater than pi by 2, right? And the left case which we have drawn is Ig at less than pi by 2. Yeah, so somebody said thyristor. Who said thyristor? Okay, so are you guys aware of thyristor? Not much. So that's okay. We'll talk about it later. That's fine. I just thought that if you have learned it in the previous class, then we can associate it. Yeah, but this is actually like a thyristor. We'll come to that later. Any question in this basic waveforms? Anyone? So what it can do is, what this semi-controlled device can do is, we can change the average output voltage, right? Depending on the where we fire or where we provide the gate pulse, we can change the average output voltage. If I provide gate pulse at pi, my average voltage, output voltage will be negligibly 0. If I provide it at pi by 2, it will be the average of one waveform. If I provide at 0, it will be the average of another waveform. So by varying Ig, I can change the average output voltage, right? Okay, so that's the use. Basically, if you had diode, you had no other option, your average voltage will remain the same. Here you got some control over the average output voltage. Okay, now let's come back and let's try to answer the other question which was asked, that what if I provide Ig at, let's say, greater than pi by 2, hypothetically, right? So let's say this was the input voltage, yeah, this is input voltage, and I want to draw the output voltage, and I am providing Ig at greater than pi by 2, which is at this instant, and of course I will provide it again in the next cycle also. How would you draw the output voltage waveform? Can you please give it a try? Draw it in your notebooks. The output voltage waveforms. If I am providing a signal Ig only for a short duration, so when I draw this Ig peak, what it means is, in this short duration I am providing a positive voltage or a positive current. In the remaining duration I am keeping the grid to a negative value, right? In the small duration I am providing the grid with a positive voltage or a 0 voltage or a positive current. Remaining duration I am keeping the grid to be a negative value. So the ignition of the generation of the arc cannot start when your voltage is negative, right? Because the electrons will not start flowing. Once they start flowing, then it doesn't really matter. So can you now draw the output voltage waveform? Yeah, try to draw the output voltage waveform. This could be a quiz question. So just start from t equal to 0, right? You can imagine that at t equal to 0 also, since this is sinusoidal, there would have been another, you can imagine there would be like this kind of a waveform. There would have been provided a gate pulse here. So you can figure out what is happening at t equal to 0, right? Would the device conduct at t equal to 0 is the first question, right? Because every time we start at t equal to 0, then we start drawing, right? Would the device conduct at t equal to 0? How many of you say yes? How many of you say no? Oh, good. So most of you could understand it. Yeah, the diode device will not conduct at t equal to 0, but I gave a gate pulse at some time before it, right? I gave a gate pulse here. So why a device will not conduct at t equal to 0? Because I gave the small gate pulse here, but at that time the anode to cathode potential was negative. So even though I removed the barrier, grid barrier for some time, but there was no conduction because the potential applied was reverse bias, right? So nothing happened there. I removed the grid, nothing happened, I just placed the grid again at that instant itself, right? So the device was off at t equal to 0, even though now I am trying to apply positive voltage because of the grid, there is no conduction, right? So it will remain off. So the output voltage will remain like 0, it will remain 0, it will remain 0, it will remain 0, and then what? So pulse is little bit far away, I am at t equal to pi by 2, t equal to pi, right? Now the voltage has become negative. So anyways, I mean, even if I later on provide a pulse, nothing will happen. So it will remain 0, it will remain 0, it will remain 0, it will just remain 0 everywhere, right? So output voltage will be just 0, nothing else. Is that okay? Can you repeat the question? Let me try to repeat the question, that way it gets recorded also. So what he is saying is that whenever I remove the grid, or by removing the grid, maybe I give it a positive voltage, or imagine maybe physically I am removing it or something. At that moment, this behaves as a diode. So at that moment, if I have anode more than cathode, then the electrons from this pool of mercury would find a way to the other side and they would create an arc. But if I remove the grid and the anode to cathode is still negative, then the electrons will not go there, they will just stick to this place, right? So the arc will not get formed. So for arc to be formed, you have to have both conditions simultaneously getting satisfied. One, removal of the grid, and secondly, anode to cathode potential to be positive. If you have both together, then the arc will form. Once arc is formed, you know what happens after that. Bringing the grid will not help you much. So to start conduction, you should satisfy both the conditions together, and first condition is VAK should be greater or equal to positive, and second is that IG should be positive, right? So if you have both conditions happening together, your arc will get formed and your conduction will start. And to start conduction, you have to simultaneously meet, or this can be also known as arc forming. Okay. Any more doubts? Okay, so she is asking what happens if you give the pulse just before the rising cycle. Now just before is very tricky, right? If you give just before, it will start, but if you give just before, it will not start. You got the answer, right? Yeah. So basically, I mean, you should have at that moment both Ig positive and Vak positive will start. Yeah. So if you can do that, okay, that's a good choice, right? What he's saying is like, why are you giving this pulse of Ig, right? You can keep that current or the voltage going into the grid positive for some time. Fine, it will not have much effect, right? For instance, here I could have done is, let me change the color of the pen if that is a possibility. Oh, that's a possibility, great. So instead of doing this, I could have done like this, nothing would have changed. Instead of doing this, I could have done Ig like this, nothing would have changed. right? I could have done this, nothing would have changed. Of course, if this, in practice actually you would not give a single pulse, you will give for some time. So that would not make much of a difference. Of course, if you keep that pulse itself wide enough equal to 2 pi, that means you are giving Ig all the time. Then the whole thing changes, right? Is that okay? So you can give for some duration, but that should not be large enough to interfere with the next cycle, right? Okay. Let's move on and let's look at why do we study these things, what is the use case, right? Of course, today I can relate it with the phone. I was telling you phone's example that you need a DC output voltage, so you need a rectifier, right? All of those things. But when we are talking about, let's say 1950s or even slightly before that, you remember there was this Tesla versus Edison story which we keep coming back to. So if you have not read about it, go back and read because we'll keep referring it to. Was in 1890s, right? And there was a demonstration of a small street lit by DC supply, right? So there was a hydro generator very close to it. There was a stream of water that produced electricity, and that electricity was used to light up that street, right, with bulbs. This was in before 1900s, right? Of course, another 50 years now people started using electricity, right? But it's not possible that every time I have to go and live next to a flowing river, right? That's not possible. So let's say I'm staying in some place, but there is a river someplace else, and so there is a generator there which is producing an AC voltage. AC became famous, right, after 1900s. Now, how do I bring that voltage, AC voltage which is getting generated there from that point to the point of load, right? So you have, let's say, this river which is flowing, and this is where you live, right? And you have an AC generator here, it's producing AC voltage. Now you have to bring it somehow to your home, right? If it's 1 kilometer, maybe okay, 2 kilometer, it is okay. What if it's 100 kilometers or it's 150 kilometers? If you generate, let's say hypothetically 400 volt, right, AC, and if you draw such a long wire, the voltages will drop, right, and eventually the voltages which you will get here may be very, very low, right, which you don't want. If some of you have, I don't know if it happens now, but at least 5-10 years back, right, you would have, you could sort of, if you go to a remote village, right, a place which is really far away, and getting power supply from little far away substation, then the voltages at the receiving end or at the load end would be very, very low, right? They will not be 400 volt 3 phase, they may be, maybe just 200 volt 3 phase or something like that. So this voltage will drop, especially if you have lot of load, right? You have so many people staying there, then there's more current, so more drop. So what people did is, and that was in 1950s, right, 70 years back, people knew about transformers, right? So what people thought is, okay, we'll step up the voltage and then we'll send it and these guys can step it down, right? It's the simplest way, you already know it. So what I can do is, I can step up this 400 volt into relatively higher voltage, then I can step it down and then I can feed the house. Yeah, that's a possibility. There are certain challenges in doing very high voltage AC transmission, right, over a longer distance of time. And those challenges we'll study, subsequently towards the second half of this course. But there are challenges in long distance AC transmission. And therefore, people thought that, let's try to use a combination of AC and DC. Let the generation be AC using a synchronous machine. I will pass it through a box and convert it into a DC, and that DC will run away over a longer period of time. I will pass it through another box which will convert into AC, right? You remember these symbols? And this can go to the load, right? This kind of arrangement is called as HVDC, which you can guess means what? high voltage DC. And this is the place when you want to rectify from AC to DC, you require controllable diodes, so to say, or those semi-controlled switch. So this was the first place, a predominantly major place where those mercury arc walls or mercury arc rectifiers were used, right, in reality. Okay, so what he's saying is that isn't it better? I mean, that's why AC became popular, because it was easy to transmit over a longer distance. But then now we are again talking about DC. Yeah, that is a bit. You may feel like it's a bit funny thing, and it's true also, right? So if you want to generate power, right? DC machines are not good because they have these brushes and commutators, more maintenance. If you have a synchronous machine, you can do it much effectively, right? So you can generate AC very easily. You can send an AC power to a relatively nearby places easily because you have a transformer. You can step it up to 11 kV, that's what, or 22 kV, that's what the system we have in our campus. And then the power can go from one point to the other point. It can go from one station to the building and so on. But if you want to transmit power over very long distance, right, then there are challenges because of the reactive power involved, because AC always have reactive power, and because of that there are some challenges which we will talk about in the second half of the course. And therefore, yes, if you want to do a very long distance transmission, then ACs were not preferred. It was easy to do DC transmissions. So the generation was AC, the load was AC, the long distance transmission is DC, not the short distance. Short distance, it's perfect to just step it up, transmit, or rather distribute it, step it down, use it, right? Yeah, so that's, I mean, the world is strange, right? So that's how things happen. This is one of the early, not the first one, but this is one of the early examples of a high voltage DC transmission system. This is a snapshot of Canada. This is the Manitoba province, right, which is highlighted in little light yellow color here. And the red line which you see is the high voltage DC transmission line. The power generation happens here. If you can see, there is a river here, right. So this may be the right place probably to do the power generation, because there is large amount of kinetic energy the water would have gained, and so on. And then you generate AC power. Of course, you convert the AC power into, you step it up using transformer, then you convert it into high voltage DC using mercury arc walls, and then the DC power flows in this direction and it comes to a place called as Winnipeg, which is a reasonably big city, right, where the loads are, and then again it gets inverted into AC, steps down using transformer, and then you can again use the same voltage levels for residential and commercial applications. So finally it lands up here. Lot of people living here, not many people living here, right? The population densities are certainly different. So there is a source of power, but you actually need the power here. So this is what you can use to transmit the power. This is about 890 kilometers long, right? 890 kilometers long. How much is 900 kilometers? From Mumbai, can you name any city which is about 900 kilometers? Okay, maybe Bangalore. Yeah, maybe, I'm not sure, but yeah, looks like Bangalore probably. Yeah, okay. The transmission was happening as 150,000 volt DC, right? And that's why we call it high voltage. It's not 150 DC, it's 150 K DC voltage, right? So 150,000 volts flows from this DC line or cable, right? Yeah, question? Yeah, okay. So what he's saying is that the architecture which we just saw, right, you have AC, then you do step up, and then you do the rectification, right, and you get DC and then you send it, right. Instead of doing that, why don't you eliminate this transformer and you convert this AC into DC and then step it up in the DC itself, maybe using a DC to DC converter, boost converter or something like that. So look, there are quite a few practical reasons why that doesn't happen. It didn't happen at that time, and even today that doesn't happen so much. At that time, why it didn't happen, you can clearly see, right? You don't have that kind of boost converters. Boost converter cannot operate with the same switch, by the way. It requires a fully controlled switch. That time, you didn't have a fully controlled switch. Even today, you don't have a fully controlled switch which can handle 150,000 volt. So there are a lot of practical challenges in doing it. It may be more expensive also if you try to do it, right, as compared to stepping up an AC, which happened with transformer long back, and even still it's quite popular to do that, right. So I'm not saying it's theoretically it's possible. What you are saying, you can eliminate the transformer, you can do AC to DC and then step it up, but practically at that time it was probably not possible. Today it's still possible, but I think that would be much expensive and much more challenging. Maybe it will happen, or maybe it is happening, I'm not sure, but it's not very practical thing to do, because transformers are still cheaper in a way, right? Errors are okay, that's fine. You can always have control. We'll tell you, like you can always control the DC voltage, you can control the gate current, you can manage the output voltage, you can regulate it, right? That's what we just saw. Okay, any other question before we move on? Transmission. Yeah. So you see, initially, I mean, I'm just trying to answer it. I'm imagining now. Initially, people started figuring out there is electricity. You can light a bulb. Fine, you know, there's a stream of river flowing from 2 kilometers away. Let's power something, step it up using transformer. Let me get it, right? Which is okay. But when we talk about, but when a high voltage is a relative term, right? When you want to transmit power over hundreds of kilometers, then AC was not as good as DC, right? But the initial requirement may not be that, right? Early 1900s, you were not thinking of transmitting power from such a far away place, right? You are thinking, okay, in my radius 5 kilometer, 10 kilometer, I will generate, I will step it up, step it down, use it, I am happy. So both things happened together, right? The need for power increased, plus you had these devices which can actually do AC to DC rectification, controlled way, semi-controlled way, right? So if you see, although the invention sort of happened in 1900, 1902, but then they may not be capable of handling such large voltage just when they were invented, or such large current. So the technology would have evolved in this case also. So there may not be a need for doing a very long distance transmission, and there may not be devices capable of doing that. And therefore, at a later stage when both things happened, people started moving towards that. Yeah. So both very high voltage transmission, very long distance transmission happens through high voltage DC. Of course, things have evolved there also, but yeah, I mean, broadly speaking, it's high voltage DC, and any shorter transmissions happens through AC. Of course, both technologies have improved over a period of time. Okay, this is a picture which I took from, so this shows those rectifiers. I don't know, it's very difficult to associate them with the lighting bulb which we saw. But you remember there was two types of it, right? One was bulb type and the other one was with a steel container. Steel container was easier to transport, it doesn't break out, it doesn't glow, so it doesn't look that fancy. So these are the ones with steel container. So basically things are happening inside it. The basic principle is the same which we saw in the bulb case, but it's just that it's not visible that easily. And this on the right side is a table which was published in an IEEE magazine article, Power Energy magazine article, in their history section, and this gives you some of the early high voltage DC transmission setup. And you can see the first one in this table I can see is on the top. So this is in Sweden in 1954, right? The transmission distance is about 100 kilometers, 96 kilometers. The one which we saw just now is at Nelson River Bipole 1 in Canada, where the distance is about 890 kilometers. And you can see there were many more, right? There's one in USSR, New Zealand, Denmark, to Sweden, Japan, Italy, Canada, US and so on, right? South Africa, UK, Canada. So, you can see right from 1954 to 1975 there were at least 10 of them and they continued to build. Only thing to notice is the wall type, right? So, they were MERC stands for mercury arc wall. So, they were using, earlier ones are all using mercury arc wall which we saw, and later on they shifted to THY which is thyristors, right, towards the end of towards 1970s, and after this the mercury arc wall sort of vanished and everything was built with thyristors, right. So, we will see what a thyristor is as we move forward, but this was like one major change. So, mercury arc rectifiers were popular till 1960s, mainly for various HVDC systems. Okay. So, around 1950s is when this sort of semiconductor thing started, right. If you see, mercury arc wall was not sort of a semiconductor, it was, but it helped in conversion of AC to DC, but it was still not a semiconductor. So, the main semiconductor era sort of, so as to say, for a user it began from 1950s or so. 1947-48, you know that BJT was invented at Bell Labs by Bardeen, Brittain and Shockley, right. And then there are so many stories, you can go back, you can Google, you can read, right. There are so many interesting stories around all these inventions and all, right. Anyway, so BJT all of you know of, right. It's not of much use for processing high power because these are not available in very high voltage and high current. These are low voltage and low current devices, right. This is a typical symbol of a BJT you see on the right side. These are some of the packages, I mean, this is how it would typically look like. They are very useful for control and signal level electronics, right, because they are usually operate at low voltage and low current, and therefore they are not very popular for power electronics, right. When you want to convert high voltage signals, you need devices which can sustain those high voltages, or let us say 400 volt, 300 volt. These are the devices which are not capable of doing that, right. So, they are not suitable for power electronics, right. They were certainly and are certainly suitable for regular electronics, right. So, yeah, you won't see much of BJT in this course. We can use BJT for control application, for signal application and so on, right, but not for processing power. Yeah. So, the next one which really sort of started the power with the electronics part was thyristors, right. So, thyristor functionally were very similar to the mercury arc wall. The only difference was the same phenomena were done by using semiconductor in a very, very small package instead of big, bulbs or something like that. So, this is the symbol on the right which I have already used when we were drawing some time before. So, there is an anode, there is a cathode, there is a gate. In terms of operation, you can imagine the mercury arc wall, they are exactly the same, right. Of course, the better performance, maybe lesser losses, faster switching, whatever, right. Better performance, smaller size, but the basic operation wise, they are same as mercury arc wall. This is one of the package which looks like, so this part here is cathode, this bolt which is connected to the metal body is anode, and these are your two small pins, which one of them is gate and the other one is cathode, right. So, this is the two small pins you connect to a small electronic circuit which provides a gate current whenever you want to turn this guy on, and the main power flows from these thick conductors. You see the main power, there are very thick conductors from the main which carries hundreds of ampere of current, right, or maybe thousands of ampere of current also. So, this is how a typical rectifier looks, but there are different packages. So, it is not that this is the only way a thyristor can look like. Thyristor can be packaged in very different ways. This is one of the popular thyristor packages, especially last 20, 30, 40 years. This was around 1956 again at Bell Labs, and this was commercialized by GE in 1958. So, you can imagine 58 it came, and then slowly people started using these guys instead of using mercury arc was when they were building the HVDC systems, right? Would have taken, let's say, 5-10 years for technology to mature before people started using it, HVDC systems. Okay, use case very similar to mercury arc wall, right? This is the one which sort of brought power into the electronics framework. The BJTs we saw were not really useful to process power. What are the characteristics of these devices? This is the symbol, right? This is anode A, this is cathode K, this is gate G, this is the gate current IG, this is the anode to cathode voltage, and this is, let's say, the anode current, right? This is the rough structure. What is the characteristics? Let's say if I draw VAK and this is IA, okay, and if I talk about ideal device, right, if I don't apply the gate current, then this is like open circuit. If I don't apply the gate current, then the anode and cathode terminals are like open circuit. Current cannot flow from anode to cathode, current cannot flow from cathode to anode. Cathode to anode anyways never current can flow, right? Anode to cathode only current can flow, but if I don't apply gate current, there is no possibility. When there is no gate current, then this is how the characteristics look like. So, irrespective of you apply 5 volt, 10 volt, 15 volt, there is no current, IA is 0, right? This is the open circuit. Is that okay? All of you understand this way of drawing the characteristics, right? So, you can see that even if I provide 5 volt, 10 volt, 15 volt, 20 volt, my current is 0, and I can provide minus 5 volt, minus 10 volt, minus 15 volt, current is 0, right? Of course, I cannot provide, I have to see what is the rating of the device. So, if the device is rated for 100 volt, I can go up to 100, I cannot provide 1000, otherwise it will get damaged, right? So, I have to see what is the maximum the device can take, but in that region I can provide plus and minus, it does not conduct if the gate is 0. We call this as, let us say, off state, okay, which is Ig is equal to 0. If I provide a gate current and there is a positive voltage, the current will flow, right? The device will behave as a short circuit. It will have some resistive drop, but that is very, very small. So, ideally, this is how the characteristics would look like, and this is what I will call on state if Ig is positive. Okay, so as soon as I provide a gate current, and then even if you provide slightest amount of positive voltage across anode and cathode, it will have a positive current flowing through it. It cannot still have negative current, right? There is no possibility of negative current. So, if you apply negative voltage, it will still have 0 current. So, this is how we can say an ideal thyristor characteristics look like. Yeah, correct. So, if Ig is 0 for that moment, it will start like a diode. Once it is on, you know the characteristics, right? This is the characteristics when it is on. So, the off characteristics is horizontal line, the on characteristics is this vertical line, right? And you know when it will turn off, right? As soon as the current becomes 0, it will then come here. If you next time again you apply gate current and you have a positive voltage, again go there. Very similar operation as that of the mercury arc wall. Is that okay? Any doubt? Any question? Okay. Yeah, so this is something which I have drawn before, the same diagram, right? In the off state it is horizontal, in the on state there is this vertical line. Basically it allows current to flow in one direction when it is on, still does not allow current to flow in the reverse direction. By the way, thyristors are also known as SCRs, which stands for silicon controlled rectifiers, right. So, thyristors are also known as SCRs, just a different name. Okay. So, what he is asking is if Ig is positive, will the thyristor always have a fixed value of IA or can it change? That's a good question. So, I think what he is trying to say is whether I am operating at this level or this level or this level, where I am exactly operating, right? How do I figure out? So, let us go back. Yeah, let us come back to this case, right? When the device is on, that means in this region the device is on, this could be a thyristor, right? At each instant, what will be the current? Current will be output voltage divided by the resistance. So, the current is actually determined by the load. The value of resistance combined with the output voltage determines the current. So, you will be in the vertical axis, where you will be depends on what is your load, what is your source, what is your system, right. So, therefore, there is no one point. I have drawn these characteristics as lines. Basically, you can be anywhere depending on your rest of the circuit. Okay. In reality, things are little bit more complicated, right? And I will try to explain it. If you can absorb it very well, if you cannot absorb it, we will try again next class. Yeah. In reality, the characteristics looks a bit more messy, the one on the right side. We will try to simplify it. First of all, you can imagine yourself if you can do a mapping, right? If you can correlate the ideal one with the actual one, the ideal one with the actual one. There is some difference there, right? But if you can see at least, mota the actual one looks similar to the ideal one. Can you see that? Broadly, the actual one looks like an ideal one. So, if you see for example, the negative thing, right, this is same as this. At least this looks very similar to this, only it is not sticking to the axis, it is going little bit negative. What it means is if you apply very large negative voltage, there is some leakage current in the negative direction, milliamperes, right, not more than that, maybe microamperes. But more or less, this is nearby, and of course, if you apply lot of negative voltage, this device will just break down, it will just fry, and then it will be a burning device which will have current to flow, right. So, let me point out these two things. So, this is leakage current which you see in the negative direction, and this is what we call it as breakdown. So, is this negative part okay now? Any doubt in the negative part? It sort of matches with the ideal one very closely. Is that okay? Any doubt in the negative part? Anyone? Yeah. Even if Ig is 0, Ig is non-zero, the negative part remains the same, more or less. Okay? Because this is reverse bias condition, right? This is basically reverse bias condition. Now, let us look at the forward bias and Ig is 0. This was the ideal characteristics. You apply 50 volt, 100 volt, current is 0. In reality, there may be some small leakage current, more or less current is 0, there may be some small leakage current, right. So, this part is, let me call it as forward leakage current. So, now all complete horizontal line we can map, right, very similar to between ideal and real. Now, let us look at the vertical line which is in the on state. Here it is a vertical line on state. Here this is not a perfect vertical line, there is a diode-ish kind of characteristics. You remember diode characteristics, right? This is how the diode characteristics looks like, right? What it means is if you have 10 ampere of current flowing, the drop will not be 0. There will be some 2 volt, 1 volt, 0.7 volt, 0.6 volt, 0.8 volt drop depending on the diode, right? If you flow 20 amp, you will have some diode drop, right? So, the difference between this part and this part is just that there is some forward bias diode drop, that is it, nothing else. Is that okay? So, this is represents the forward voltage drop, and this is of course in the on state, that means Ig is greater than 0. Alright, what happened? Is this okay? Now if you see, in addition to these lines, there are some dot lines hanging around in this place, right? What does it mean? What are these things? What are these things? These things are sort of indicative, and what they are trying to tell you is when the device goes from off to on and on to off, right? And this is a small difference, and you may have to sort of, for device to turn on, let's say your device was here, it was in the off state. For device to turn on, you have to provide a gate current, and that also should have a anode to cathode potential as positive, right? And the device turns on. Now the current is reducing, you have removed the gate current, let's say current is reducing, it doesn't really go till 0. So if the current is less than something called as holding current, the device again turns off, right? Ideally your current can become very close to 0 and device will still continue to work, but what happens if current is very low, the arc will just vanish, right? And so at a slightly non-zero value, the device will turn off, which is what we call it as IH, or the holding current. And for the device to turn on, to arc to form, you need a little bit of latching current. Of course, in thyristors there is no arc, by the way, we are just imagining arc. This is a semiconductor device, there is no physical arc happening anywhere in this. But just to correlate with the previous example, you need some amount of latching current for the device to turn on and some amount of minimum holding current for device to remain on. So these are the two terms which are a bit new. And even if you don't remember them, that's perfectly fine. Latching current for device to turn on, and this is holding current for device to remain on. With that, let me also give one more clarification here. What you see on the left side of the screen, is part of the syllabus for this course. What you see on the right side of the screen is my enthusiasm, I bought that, not part of this course, right? So even if you cannot understand exactly what happens on the right side, don't worry, you will not lose anything. Whatever happens on the left side, you must definitely understand, right? So ideal characteristics you should know, real characteristics if you don't know, this is a basic course, that's perfectly fine, you can learn it later on, right? Okay, I think with that, let's stop today's lecture.